Well, good morning. Good morning, everybody. It's my name's Rob Clayton. I'm the director of the Traffic Management Division at UDOT, and it's my pleasure this morning to introduce this session about managed motorways. This has been an interesting process to get to this point with this project. The title of our project probably catches your attention because we're using strange words. Motorways is a reference to the project that originated in Australia. It's been a fun process to work with the folks from Australia and to interact with them. I love talking to them because of the way they talk, but they're really brilliant folks, and they came up with a great concept. And like UDOT has done in many other instances, we're looking to duplicate successes in other places and pursue those here. So that we're here to talk about freeway operations and some new ideas that might that we expect to improve things here in Utah. We've got a great project team that's been attacking this, led by Lisa Zundel from Region 2 and Eric Rasband from my team, and Diego Carroll from the Parsons Brinkerhoff team. And we're excited about this project and hope that we catch your attention and spark your imagination. And if you have questions or comments, make sure you bring those up. I think they want to handle those at the end, but we hope you enjoy this presentation. So. One last thing. I always make sure you keep your name on here if that's important to you.
All right, as we were having people filter in, we were playing this video in the background. This video is developed to kind of show the concept at a very high level of the managed motorways. We'll just run through it real quick and then move into the presentation.
Every day during rush hour, hundreds of thousands of vehicles enter Utah's freeways, many of them at the same peak times, and this can cause hours of traffic congestion. As Utah's population continues to grow, even more cars will be on the road. The question is, how can we reduce traffic congestion? Well, UDOT may have found an answer through managed motorways. To better understand the problem, we're going to demonstrate using PASTA and a funnel. The PASTA represents cars as they are trying to enter the freeway, while the funnel represents the interchange itself. During rush hour, vehicles pour onto the freeway all at once, and it doesn't take long for traffic to back up. But if we control the flow of traffic, only allowing a limited number of vehicles to enter each interstate at one time, traffic moves much smoother with fewer delays. Comparing the two shows that more vehicles can get through in a controlled situation than if they attempt to crowd through at the same time. UDOT is looking to implement a system called Managed Motorways to control the number of vehicles entering the roadway while still keeping traffic moving. Managed Motorways use smart technology, including freeway-to-freeway metering and real-time traffic information. This improves safety, reduces stop-go travel, and provides predictable travel times. For more information, please visit us at udot.utah.gov.
All right. So first off, I wanted to start off by letting everybody know Lisa Zundell really wanted to be here for this conversation, but she's busy doing another presentation in one of the other rooms. So she apologizes for not being here. But as we move forward, we wanted to talk about managed motorways, and I guess we termed this technology managed motorways. It's been some people have described it as aggressive ramp metering, intelligent ramp metering. It gets confused with some terminology used in the UK where they use motorways as well. And this is really the system developed in Australia, which is different than the other systems that are out there that may use similar condition or similar technology or terminology. And so as we're moving forward, we're going to talk through the concept, talk through the study that we completed, and then some of the conclusions as we're moving forward. So Australia, they were about where they were 10 years ago about where we are, where they had a very aggressive building program, and they came to a realization that they couldn't continue to build their way out of congestion. And so they started looking at technological solutions. John Gaffney with Vic Roads, the state of Victoria, or Vic Roads, which was equivalent to UDOT, applied for a grant that their organization has. And with that grant, he used the money to travel the world, and he was able to make contact with some physicists in Germany and professor at the Technical University of Crete in Greece that had looked at metering at a very microcosm level, basically at 20-second intervals, and tried to look at how they could expand their capacity, the roadway carrying capacity. And through that visit and through the contacts that he made during that time, he developed this system with help of a lot of consultants and a lot of staff and resources, and over the last 10 years has taken that initial system and has refined it and added additional algorithms to the ramp metering system to the point where there's a lot of success. So as we go through this presentation, a lot of this is the experience that Vic Roads experienced, and then we're going to pepper in some of the information that we know about our system. So as they were looking at their system, they knew that the freeways were one of their highest assets that carried a lot of vehicles. They started looking at traffic volumes along their corridor, the M1. And in 2000, they were carrying 2,000. In year 2000, they were carrying 6,000 vehicles out per lane in a 3-lane facility. Sounds reasonable. The textbook says 6,600. In 2003, the volume started to reduce. 2004, 2005, 3,900. And so the question that they asked themselves, did we have the right data in 2000? That downward trend just suggested that, yeah, they did. And as they were moving forward, they started to see a degradation in the performance of their freeway system, similar to what we're seeing in our system as well. So, so what they knew at the time is the unmanaged freeways were performing the worst when they needed them the most. So if we compare this to our system, we run ramp meters today, but during our peak congestion in the PM peak hour, our main line I-15 will break down to carrying about 1,300 or 1,400 vehicles per lane per hour. And so their system is looking at how can they carry more and using the technology, and we're asking that same question, looking for technological solutions rather than civil building solutions. So what they believed was that they can perform their best when they're needed the most. So some of the objectives that they established are very similar to the objectives that we have. They want the freeway to be a safe freeway. They want to maximize the a number of vehicles to get through. They want to improve travel time, reliability. Reliability is a metric that we're hearing a lot on the national stage, and reliability, we can have a corridor that's performing very badly from a speed or differential, but you can reliably plan on that route being bad. And their goal was to reliably have a good performing corridor, so it would serve the public to the best that it can, and then balance their access and mobility throughout their system. So it's key that you know that they are not focused on maximizing speed through the corridor. They're focused on maximizing the number of vehicles through a corridor. So their system, they're managing what is equivalent in ours, about 45 to 50 miles an hour is when they're getting the optimal throughput through their system. So just a little bit of a background. The M1 is a major east-west freeway that goes along the port of Melbourne, has a heavy truck percentage, somewhere in the 30-40% during the peak hour. So just huge traffic volumes and truck percentages through the corridor. Gives you a little bit of perspective, understanding. It was a 3-lane facility. It was, as part of this project, was widened to a 4-lane. So they carry, well, we'll get back in. So the M1, in relation to the train, their transit system was much more diverse and more developed than ours is. We've got a great transit system. But their transit system carries a lot more people on it than ours does. The M1 still carries significantly more people, which is similar to what we see on I-15. So they took a measure along the M1 of how many vehicles are getting onto the freeway, and they added all those vehicles getting on. We've done the same comparison on our system. They recorded 850,000 trips during the day. During the day, we record about 650,000 trips getting onto our system. In relation, you saw some of the volumes, 220 to 280,000 trips, ADT trips. That's a metric that a lot of people understand a little better. Our system, we're at our busiest, is about 260,000 AADT. So, how does the M1 relate to the arterial system? The M1 carries a lot of traffic. You look at the adjacent arterials, and they're important, but they carry not quite as much. So the M1 is 2% of the lane miles in their system, but carries about 15% of the urban travel. We haven't run that statistic, but we believe that that's very consistent with ours, where I-15 is a major carrier of the peak traveled throughout the day. So this is a graphic that John took standing on an overpass looking, and you'll notice down here at the overpass in the other direction, there's a lane drop that's going to go, and we're just going to step through a series of photos here quickly to see what happens with the peak travel and how congestion builds. So 1 minute later, start to see some fill-in going on. 2 minutes, start to see some congestion, brake tapping, lane utilization because of that lane drop. They're starting to get over into those 3 inside lanes, brake lights, and basically 6 minutes into it, this is standing on that same overpass, just turned in the other direction. We see similar issues on the SR201 to 215 southbound merge, the 215 to southbound I-15, the SR201 I-80 ramp to southbound 15. We see that same type of breakdown, and it occurs in about a 5 to 6 minute window. So we're starting to compare their system and see that, yeah, our system's performing in a similar fashion. So they were like us, where we had some great ITS tools that existed, variable message signs, CCTV, variable speed limits, ramp metering systems, and they were getting as much as they could out of their system with the tools that they had available, but they felt like they could do more. And so they had the conventional ramp metering. The delays, some of the benefits of ramp metering that we see is it delays the onset of breakdown, but it will not prevent it. Speed recovery helps, it helps speed recovery, and helps to shorten that peak period. It increases the throughput by between 2 and 10%, but it still doesn't deliver that 2,000 vehicles per lane per hour that we'd like to see and that we know the freeways can carry. Ramp metering has been documented throughout the country to help reduce crashes, and we know that that helps, and then it helps improve travel time reliability, if only lightly. So as we move into managed motorways, a managed motorway is not necessarily just a freeway or a motorway with ITS devices and a traditional TOC. It's using the most out of what you have available, and the accuracy of the ITS devices, specifically the vehicle detection, Diego's going to get into that a little bit, is much higher than what currently exists on our system. It applies contemporary traffic theory, new design standards for the ramps, exits. As we get into the results, you're going to see that the system's very good at providing more vehicle throughput. You get more vehicle throughput, then you're going to start delivering those vehicles to the off-ramps. And what do we need to do to the off-ramps to design for that additional demand that we're going to see? And the use of data and collection. Mark Taylor in the previous presentation talked about measuring data or using data to measure how you're performing. This system is heavily involved in taking advantage of the data that's available and looking at it and making adjustments as necessary. So in a nutshell, system-wide control, all ramps must be controlled. That means the system-to-system ramps. So the ones that we talked about, 215 to I-15, SR201 to 215, SR201, I-80 to 15, those all get a ramp metering. Now, it's not unprecedented in the U.S. for that to occur. California has been running this system-to-system ramp metering for 6 years. Minnesota's been running that. So we're hoping to get over to those agencies to learn some of the lessons that they've learned in that process. The system requires a lot of vehicle detection at a high level of accuracy. And then the meters will monitor mainline and will turn on automatically up to 20 or more times a day. And the meters will stay on for a minute, if only needed for a minute to address the congestion, or it'll stay on for multiple hours based on the flow and the demand of both the ramps and the main line. The system starts by working as one individual ramp, but then if that one individual ramp can't address the congestion at the bottleneck, it asks for help from the upstream ramps, up to 10, 15 ramps in advance of where the bottleneck is, and helps adjust the metering and the flows into the bottleneck. The queues are managed across all of the ramps. So if you run, for instance, 106 South, where we have a huge volume getting on, there's a possibility that we won't be able to store all the vehicles at 106 South, so we would engage 114th, 123rd, Bangerter on down the system to help manage the storage throughout the system as well. And then it's really set up for equality of access, so everybody shares the pain throughout the system, and we try to balance that delay for everybody. So let's get into the data. So the red line is the system that Victoria ran prior to the implementation of their managed motorway system. It was a conventional ramp metering system similar to ours. See, the volumes would go, and then, the green. I'm sorry, it's the green is the system prior to the ramp metering. The red is after the managed motorways system was installed. Basically, they didn't allow their system to go to breakdown, and you can see they're serving big volumes during the peak hour. That represents the 25% increase in vehicle throughput carrying capacity along their corridor. That's equivalent to basically one lane of the freeway. So how does that compare to our system? This is I-15 just south of SR201. in between 201 and 3300 South. The red line is the traffic volume, the blue line is the speed, the green line is an occupancy, which is a measure for the detector. But what happens is the vehicles come along, we see little spikes in traffic, and then all of a sudden we see a huge spike. And at that point, we see failure or breakdown occur on the system. And we see the volumes drop, and then through the rest of the peak hour, you can see the speeds drop, the volumes drop, and that's kind of how we're managing our system during the peak period. That results in about 1,800 vehicles during the peak hour that we're losing of vehicle carrying capacity on I-15. 18%, 1,800 is also pretty close to what a freeway lane should carry. So there's some opportunity for us to gain vehicle capacity with technology. So many of you may have seen charts or curves similar to this. This is published out of the textbook published by the physicists from Germany, representing the data. HDOT is a detector input of vehicles coming in. You can see the volume or the speed of the corridor, the volume. Basically, you're going along at 60, 70 miles an hour. Things are going good. You see a little spurt, and then we see the breakdown, that other spike that we saw in the last graph. And the volumes go down, you start seeing lane changing and the ability to carry traffic. So we manage our system kind of in this area. This is our data. So we see that traffic moving along, we see the little spurt, and then we drop back. Let's see, the blue dots are the actual failure that we measured in our system and when the volumes and the speeds drop. So we see our speeds come in and we see this little spurt, things are going on great, congestion hits, we start drop, and we manage our system in this area. So lower volumes, lower speeds, and there's an opportunity. In order to recover, the volumes have to reduce so that there's ability to pick up speed, and that's what this orange is that recovery curve. So our goal would be to manage in that optimal level where we're getting optimum speed, optimum vehicles through the system. So we've talked about capacity and the benefits of the system. The system in Australia was really focused on safety. When they sold this to their legislature, to their constituents, safety was the conversation. It was not capacity. The safety culture in Australia is much different than ours. In the early 70s, they required airbag deployment on their vehicles. I think ours was in the early 80s. They have automated speed enforcement with radars. If you're doing 3 kilometers, the conversion rate for 3 kilometers to miles per hour is 1.9 miles per hour. If you're doing 3 kilometers over the speed limit, you're eligible to automatically get a $300 speeding ticket. And that's what happens. So their highway patrol is not on the interstate system to enforce speed, is there to address safety-related issues. The benefits that they saw from this system is a 31% reduction in crashes overall. The exciting thing for us is down in this area, these little dark bars are the actual fatalities that they saw in their system. So on their 16-mile segment of their freeway, or their 40-mile segment of their freeway in the last several years, they've had some 0 fatalities. We compared that to our 40-mile segment, to our 16-mile segment, and in the last 3 years, we've experienced 6 fatalities per year in that same segment. So if we could reduce the number of fatalities in that area or even eliminate them, what a great thing for the drivers of I-15 itself. So next, Diego's going to go ahead and talk about the study itself.
Thank you, Eric. Again, my name is Diego Carroll, and I am the consultant project manager for this effort. We were lucky to have a very qualified team. Rob mentioned earlier some of our partners from Australia. Eric and I looked at this presentation on Monday, and there's quite a few typos. We stole a few of their slides, so if you see any typos, it's not misspelling, it's just different English that we were using. So. But we did have great involvement from WSP Parsons Brinckerhoff on the rent metering specialty, and freeway management side of things, and from Pine Top on the ATMS capabilities here locally. And then we did take advantage of some great expertise from Australia, and then also from the Technical University of Crete that were engaged in our project, in our study. Because the concept is new to Utah and also to the United States, we actually went through quite a bit of pain to make sure that our results were reliable. So our study included first a literature review to look at the state of the practice throughout the United States and see what other practices in rent metering and freeway management might apply. We also took advantage of our overseas experts and completed an assessment of the study corridor, which really focused on I-15 in the Salt Lake County area. We also did some modeling. On this map in the orange, you can see we did some macroscopic modeling of the southbound conditions from downtown to about 90th South. And then one other component of the study included a week-long workshop where we had about 30 professionals from UDOT, from the consultant team, from other states, from Australia, three folks from Australia come together and work through the specifics of managed motorways and also of the corridor. So Eric mentioned that rent metering is already in place along the corridor. You guys see it, it's in place, you guys work with it. But it hasn't been successful actually avoiding breakdown. We still see breakdown on I-15. VIC roads in their system have been able to successfully prevent traffic flow breakdown. So because we have limited time, I would like to just focus on these 4 key factors for actually implementing and operating managed motorways. All of these are critical. Let's see, I'm just making sure I'm not missing something I was going to tell you. So let me start out by talking a little bit about access control. Eric mentioned, talked a little bit about this, but let me start by sharing an analogy that we used about controlling the crowd size of a football stadium. And because I'm a graduate of BYU, I thought I would go ahead and include in here a picture of Rice-Eccles Stadium. So there's a long story behind that, I guess, but if you have 45,000 fans at the stadium, you're at capacity, you're set up to actually have a pretty exciting and energetic game. If you bump that up to 55,000 fans, you're going to have people standing around all over the place. People will be standing on the sidelines, and people are not going to be very happy. Take that up to 70,000 fans, and people will be standing on the field. You're just not going to be able to have a game, and people are going to be really, really upset. So to manage the crowd in a stadium, you have to have gatekeepers at every single one of the entrances. And the point here is what Eric mentioned earlier, is that for managing the freeway and managed motorways, you have to control and manage every single entry point, and that includes freeway-to-freeway ramps, which Eric already talked a little bit about, so I won't go too much into that. Let me just mention, like Eric said, they would actually come on automatically. They would activate based on need. And there's a couple of points to bring up. One of them is when failure occurs on the freeway, so on I-15, that actually also impacts the freeways that feed into it, the upstream freeways. So I-215 feels the impact of that failure on I-15. So those impacts, if you don't control the freeway-to-freeway ramp, so there are some negative implications to that. The other thing I'll mention is when VIC Roads first implemented the managed motorways concept, they were very hesitant to actually meter, to signalize their freeway-to-freeway ramps, so they didn't. And they actually saw some pretty negative queue buildup and traffic flow failure, so from that point on, now they actually require all freeway-to-freeway ramps to be metered on their managed motorways projects. I think the best way to show you guys, though, the importance of actually metering these system interchanges to show you some of the results from our analysis. We actually went through quite a few scenarios. I just want to go through 3 of them. So these are 3-hour results, delays, for the 3-hour peak period, southbound from downtown to 90th South. The 3 scenarios are: 1, the no control is basically today's conditions. The partial control would be applying managed motorways to only the arterials. So this would not include freeway-to-freeway ramps. And you can see on the chart over here, we see about a 5% reduction in delays. So the number of vehicle hour delays that we modeled went down by 5%. In the full control scenario would include, actually we saw a reduction of 37%. So we used MetaNet for this analysis. It's a macroscopic modeling tool that allowed us to actually include within the modeling the actual algorithm that's used. Let me just walk through the results in a couple of different charts. This is a time-space diagram for the modeled speeds. This is for the no control condition that we're looking at here. The vertical axis is the location along I-15. Again, we're looking at southbound between downtown and 90th South. And along the horizontal axis, you have the time from 4 p.m. to 7 p.m. So you have a legend over here. The cold colors are high speeds. Hot colors, red and yellow, are low speeds, congested areas. So you can see at this point right here, you have quite a bit of congestion building up. This is existing conditions. Quite a bit of congestion happening at 90th South and then spilling back upstream to about SR 201, and also, especially building up in the about 4:50 to 6 p.m. Time frame. Next, I'll show you what happens when we actually meter just the arterials. So you can see that changes a little bit. I'll go back. So some of the low speeds go away. And then these are the results of the full control. So this reflects that 37% reduction. This is some more data, same analysis, but this is showing the speeds, the average speeds for each location. So you have the location on I-15 along the horizontal axis, starting from downtown to 90th South, and then you have the speeds along the vertical axis. This chart over here on the right represents the 3-hour average, and then these include each of the 1-hour periods from 4 to 5, 5 to 6, and 6 to 7. So you have the cyan, this light blue line is the no control condition, the orange is the partial control, and then you have the full control in the dark blue. I'm just going to focus in on the highest hour. Again, the other charts that I showed you were focused on the 3-hour period, but you can see the speeds going down on average for that 1-hour period to about 25, 35 miles an hour in this area of I-15 near the I-215 South Interchange. With the partial control, we're able to reduce or improve some of the speed performance, but the blue line shows the full control. So the point of all these charts that I've gone through here is the importance of actually metering the system-to-system interchanges, the freeway-to-freeway interchanges. Without metering those, the benefit is, there's a benefit, but it's just not nearly as dramatic and effective. Okay, so that was the first point I was going to talk about. Let me talk a little bit about the algorithms. We could actually sit here and talk about this for a long time, and you guys would all fall asleep, and I probably would too. But basically, so the algorithms are formulas that are used by the traffic signals to control and manage the freeway. They take real-time measurements and to automatically adjust, activate or deactivate the system, and then adjust the signal cycle lanes to manage the freeway. So I just want to talk about 2 of the factors. And Eric actually already talked a little bit about them, so I won't go into too much detail, but one is the algorithm that VicRoads uses is this Alinea Hero software, which includes quite a few updates that Eric mentioned. I think the version they're using is 2.2, or they also refer to it as Hero Live. But that not only accounts for the exit, it accounts for the exit ramps, main line, and also includes accounts for exit ramps as well. And the algorithm also considers the system as a whole. So it actually looks at a system of ramps, not just the one ramp. So it has the ability to prioritize when you have a ramp with heavy volumes and long queues. The system has the ability to speed up the release of cars for that ramp and then actually slow down the release rate at another ramp so that way the system can be managed as a whole. And you can actually minimize the impacts to the arterials or crossing freeways. So that's the way that the algorithm at a very, very high level operates. As you increase the amount of traffic that you can serve on the freeway, that means you can actually have faster metering, you can actually have shorter queues on the ramps, and you can actually reduce the amount of impact on the network as a whole, and particularly on the arterials and the crossing freeways as a whole. So in essence, your queue storage at your ramps actually goes down because you're servicing more vehicles through the freeway. You can actually allow more traffic to come into the freeway. So as far as the ramp design component, there are two factors that are most impactful to the capacity. Those are the storage and then the ability to discharge. The storage is pretty straightforward. You just need to have enough space so that cars don't spill out into the arterial or the freeway. The discharge refers to the ability of the ramp meter to actually release more vehicles when it has the opportunity to do that. So if you only have 2 lanes at a meter, at a signal, and all of a sudden you have a lot of capacity on the main line, you have a limited ability, by those 2 lanes, you have a limited ability to release vehicles into the freeway. So you need to have enough. In some cases, 2 might be adequate. In some cases, you might need 4 lanes at the stop bar to make sure that you have the ability to but release enough vehicles to optimize the use of your main line. So this little graphic here on the right is an example of something that VicRoads has actually used in some instances when they have plenty of storage, but they need to have a little bit more capacity to discharge vehicles. Okay, the last factor I'll talk about is the detection. Detection is critical for managed motorways to operate. You need very precise and accurate data. Speed, density, and flow are the critical, they're the backbone of managed motorways. So this level of precision is a lot higher than what we're currently providing along I-15. Let me just, to wrap up, before I turn it over to Eric, let me talk just briefly about the location, the amount of detection. So there's also a need to have actually quite a bit more detection locations than what we currently have. So for the entry ramps, actually, the required detection is pretty similar to what we have today. So we provide detection at 3 locations. That way we understand the amount of demand that we have, number of vehicles we have at the entry point, and we also have a good measure of the queues building up, as well as how well traffic is moving in the entry ramp. Something that we don't include right now are the exit ramp detection. And then for the mainline detection, right now we're at about half a mile spacing, and this would actually need to have about detection on the main line about every 1,500 feet. So it's a lot more frequent. It would be, so, now we do have, detection about this location. We would probably also have 1 or 2 additional sets of detection between the exit and the entry ramps. And I was talking to Eric earlier this week, and he mentioned actually that he's been working to implement some of these criteria into the 2017 update of the standards. So I think that's it.
All right, so some of the things that we took as takeaways from this study is it's a very promising technology that seems to be able to provide a great cost to benefit for our system. But from an organizational standpoint, our organization has been heavily involved with delivery of bridges and pavement. And we do it great. You know, Carlos talked yesterday about how great we are at doing that. There's got to be a little bit of a shift as we transition into technology and operations-based projects. And so we've got to rethink our standards, our drawings and our specifications, and think about how we can use it. Oftentimes we build a roadway in 2 to 3 years, but ultimately that roadway's got to last for 15 or more years as we continue to grow. And so in Australia, they've developed a handbook that every project must go through and basically go through a checklist to make sure that as a roadway project is being built, that operations is also being included in the overall design and budgeting, all the way from project development all the way up through delivery as they move forward. So for us to deliver a project, what does it mean? It means that we would probably have to staff up with a team like any other project to help deliver the project. We will be relying heavily on consultants to help deliver a project. At the back end, it's going to require some additional resources to manage the system, including FTE, the equivalent of people. Is that going to be UDOT staff or consultant staff? I think that's open to discussion, and we'll see where it goes. The maintenance aspect of it is it takes some money to maintain these systems. If a detector fails, we can't wait and let it be in failure mode. We have to get out there immediately to correct the detection, and so that's going to require some resources and probably some budget to manage that. We have been very fortunate as we've been talking through this system and sharing it with our senior leaders. The level of support for this system is surprising, quite frankly, and well, not surprising, but exciting, in that they're very excited about this program. They are helping us with the resources necessary to understand what it means, and we believe that this project will be in our near future sometime. When that happens, we don't know. We're developing a detailed concept report looking at 2040 traffic volumes and the impacts that we would need to understand for that. And we're hoping to see some funding coming through fairly soon on that. So in summary, our highest road assets, the freeways, can carry anywhere from 10 to 20% more vehicles, can reduce the travel times by 50%, improve the travel time reliability, provide a great travel experience consistently from day to day, and improve the safety of the system overall, and provide fairness of access for everybody through the system. So are there any questions that we can try and answer? I think we're ready. So. The question is, the system operates at optimal throughput at 45 to 50 miles an hour. Have we considered variable speed limits? Yes, we have. The Australian system has an overhead lane system that assigns the speed limit by lane and dynamically through their system, and they use that to help manage the overall system. But they are experiencing their maximum throughput is in that 45 to 50 mile an hour window, if you will.
Eric, if I can just add to that really quick, the vast majority of the benefit, though, comes from the algorithm. So that's why we focused on that aspect. And our assumption is, even though they could be implemented, we did not include variable speed limit signs in our analysis.
The Australians are telling us a 3 to 5% bump, and the ramp metering is the 15 to 20% bump. So, Steve? Yeah, you look, we have looked at a very high-level planning cost estimate. We know adding mainline lanes, if we don't have to buy right-of-way, can be somewhere in the $20 million per mile. If we have to buy right-of-way, that number can jump to as high as $50 million a mile. And the managed motorways system is looking like it's around $5 million a mile. So, VJ.
What is the impact on the interchange, like, for example, what's the impact on the queues on freeway?
The question is, what is the impact to the queuing for the freeway-to-freeway system ramp metering? I have some personal experience managing the I-15 core project down in Provo and Orem during the football events at Brigham Young University. We had an event that was exiting at University Parkway, and it was when construction was heavy at that interchange, and we went from 3 lanes to a single lane, basically with just the minimum standards. And as the event opened and when we saw the huge flow of traffic volume, we experienced queues up on the University Parkway up beyond 400 West, which is a mile plus along that corridor. And we were in the control center managing the event. We had a nice little debate. Should we turn the meters on? Should we turn them off? And finally, Taylor Forbush with Orem City convinced us, let's do it. And so we said, let's do it, see what happens. And as volumes were continuing to build, that queue dropped from the 400 West intersection down to the ramp entry point from University Parkway. Why? It's because rather than vehicles fighting for position and looking for an available gap to merge in, you're providing the organized zipper effect. So on the ramps that we see that are system to system today, a lot of them that we talked about have lane drops, and so there's a lot of jockeying for position, and we see queuing out onto 215, for example. The modeling and our experience suggests that system to system queuing that exists today actually reduces with the installation because we provide that organized zippering effect. Other questions? Okay. Thank you for your time.